This tutorial is about diffusion equation in 1D, and we will talk about the source-free region in this case, and we will also look at both Dirichlet and Neumann boundary conditions. So if we look at the general diffusion equation, we have a time dependence as a first order derivative, and the space dependence, which is the second order derivative of a scalar field. And then there's a source term that appears in case there is a source or there's a generation of heat in case of temperature field. And then we have also density and specific heat and thermal conductivity that appear as constants, but these can themselves be a function of space and time. And the two boundary conditions that we can get are the Dirichlet boundary condition, where the value of temperature is given at the boundary, or a Neumann boundary condition, where the value of the rate of change of temperature is given at the boundary, or how is temperature changing across the boundary. So if we use the finite difference method, we can discretize both the derivatives on both sides of this equation. And when we have so far we haven't seen the time term in the equations, but if the time term appears, we normally put it as a superscript, and all the spatial indices appear as the subscript of the field. So in this case, if this was a three-dimensional field, this would be I, J, K as the subscripts, and N will appear as a superscript in parentheses, which indicates the time step. So here we are saying that the temperature at location I at n plus 1 minus temperature at I at n divided by delta t is the approximation of the time derivative. And similarly, you have seen this spatial second order derivative, but look at the subscript, and it's n in all of these cases. So this is the second derivative at time n. And then source term at time n appears. A little bit rearrangement will show you that you can find the temperature at location I at n plus 1 using everything else that we know at the time step n. And that would be pretty much our strategy in solving diffusion equation. Knowing everything now, we find out what's going on in the next time step. So here's a problem that we will solve in this tutorial. So consider a 10 meters long thin rod, and initially the rod is at 100 degrees Celsius, and then we have two scenarios. In one case, we just place it on top of two ice blocks, and in the second case, we only put it on the ice block on one side, whereas the other side is just open. And because we are assuming that there is no other flow of energy, so this side can be treated as an insulated edge. So in this case, the Dirichlet boundary conditions apply, and in this case, a Dirichlet boundary condition applies on this side, and a Neumann boundary condition applies on this side. Okay. And again, because this is a source-free region, if there was heating going on of this rod, you could treat as a source there as well. But in this case, there is no source, so this equation over here simplifies where we can this thermal conductivity divided by density and specific heat can be treated as a constant. So what we have is that the new temperature is the old temperature plus some change, a minor update that happens. And here are the two conditions for the two cases. In case we have both Dirichlet conditions, in case one of these is Neumann boundary condition. But if we approximate this boundary condition over our mesh, it turns out that the temperature at the 0 should be equal to temperature at the node 1. So we will use these to implement our scalar diffusion equation in MATLAB. So first of all, just remember what the discretization is, and then based on that we will develop our equations. So first of all, we define our parameters, and for the sake of usually when we are implementing these approximation solutions, we set these constants to 1, and then for real problems we change them to whatever the actual values of the constants are. So for example, for iron you will use appropriate values. So this defines our constant A in the equation. Now the length of the rod is 10 meters, so we will divide along x-axis it into 21 nodes, and we will solve this for 500 time steps. So this gives us a value of dx which is 0.5, and we have to make sure that the time step and the space step, they are they obey the CFL condition, which is the Courant-Frederick-Lewis condition. And to make sure that it is done, we assume the speed of the flow in the medium to be 1 in this case, and the Courant number to be 0.1. So this gives, if we assume these two values, this gives us that the time step has to be 0.05 seconds. So for this, we can adjust our Courant number to increase the time step, but there's a limit on how bigger this time step can be to ensure that the solution is stable. Now we also need to create the field variable. So Tn is what we will define as the field variable. Again, this has nx nodes or nx elements, and the corresponding x-axis can also be defined where there are nx elements going from 0 to 10. And now once we have all of these things defined, we need to initialize for the initial condition. So we know that at t is equal to 0, the value of temperature everywhere is 100. So we set that, and then after that we start looping through the index. So in this case, this will be 1 to nt. So let's say we do it for the first time iteration. So we save the current value of the temperature into Tc because this is going to change, and so we need to find the new value based on our old value. So we save it into the Tc variable, and then we update the time value that we are trying to find it for. T is equal to 0.05 seconds. Now for each node along the spatial axis, we have to apply this update condition. So new value, which is Tn, depends upon Tc, which is our old value, and all of these will be Tc values, and that's what we do here. So previous value plus dt times the constant times this second derivative of the previous values. So we will run this over the whole domain. First, let's look at what the plot looks like, x comma Tn, and you should be able to see that this is a straight line. Now we update this using this loop, and we plot this again, x comma Tn, and Tn, and you can see that there is still no flow going on, but we have to adjust the boundary conditions for this to happen. And in our case, the boundary condition is that the first value is 0 and the last value is 0. So we do that, we apply that boundary condition, and now we plot the again. So we see that inside we have still 100 degrees Celsius, but at the boundaries we have 0 degrees. That's the first thing that will happen, and this part just plots it. Now with these boundary conditions done, we again save our current values. So now Tc becomes our current value, and we are trying to calculate this at 0.1 seconds. We again run through the loop and the boundary conditions together and plot t comma tn, x comma tn. And now, as you can see, this is the profile has changed a little bit. So this edge is cooling and this edge is cooling while the middle is still hot. Now we can run this as a loop. I have this plot command here where I plot the values and set the y-axis to make sure that it stays from 0 to 100, the axis limits. And then I also put the x label and y label, which puts these label values. And then I also put the title, and here I'm saying that I want to know what the time is, the current time is. So this puts the current time, which is 0.1 seconds, as the title of the axis, and then pause for 0.01 seconds. So now we can run this, we can save this and run this to see what the time evolution of temperature would look like. And as you can see, it starts to cool down, and the middle part is the last one to come down, and over several seconds this continues to cool down. And we have set our iterations to 500 iterations at 0.05 time step. That would give us 25 seconds. Now for example, let's say the thermal conductivity was 2, which means that the flow through this material is actually faster than earlier. So you will see how the cooling will become much faster, and it will continue to cool over the 25 seconds. It became actually cooler than before. Similarly, you can adjust the specific heat, which basically tells us that how much energy has to get out or get into the system to change the temperature by 1 degree. So this is the Dirichlet boundary condition, in which case both sides are set to 0. Now imagine that this side is not set to 0, but we know that this side is insulated. So this side is not cooling down. Instead, all the heat is supposed to flow into this direction. And as we talked about, this translates into the last 2 nodes at this edge are going to have equal value. So here is how we will change the boundary conditions. We will say that Tn at 1 actually has to be equal to Tn at 2. So that's the left boundary condition, and the right boundary condition is Dirichlet boundary condition, which will stay the same, that the value is 0. And these are our Neumann conditions. And so we can comment out the Dirichlet boundary condition and rerun this code and see what happens. So in this case, you can see this side is cooling, but this side is cooling at the end, and there is no flow going towards the left, but all of the flow is happening towards the right side. Similarly, you can adjust the specific heat. So let's say it takes, if we reduce the specific heat to 0.1, the effect will be that the cooling will happen